Maybe to it probably. Okay. And online, everyone is here, or three people online? Is it, je dois attendre ou on commence? À votre avis, il est venu? Okay. Okay, we will start then. Okay, let's start. So today we'll talk about semi-supervised learning, few-shot learning, zero-shot learning, and unsupervised learning. All of those terms are probably new. But so just as a quick recap, last week we talked about computer vision and in particular image classification, so how to classify images. This lecture will be a bit more abstract, and we'll talk about. So last week we've seen that if we had a lot of data, so images associated with class labels, we could make models that could be trained on those data and perform. And today we'll talk about methods to try and remove this dependence on data, on labels. And this is particularly interesting in the medical imaging problems because usually you only have a few subjects and a few examples, and you have to make models out of this. And so yeah, these methods allow us to reduce the amount of labels that we need to train our models. Again, we're going to focus on images and mostly. But these methods are, I mean, you can transfer that to any other thing. They're quite general. So as a quick reminder, for supervised learning, we have some data sets which have, so in this case, images and category, and you would have many of those in your data set. And we've seen that the size of data set matters, and the bigger we have the data set is, the better the performance of the model will be. And one big question is what costs the most when building a data set for supervised learning? Is it access to data or access to labels or categories, in your opinion? 50-50 cents. Random guess. Okay, so yeah. What cost is obtaining labels? Why? Because so images, probably you can find a lot of them either online or I mean, if we're talking about natural images, so pictures of people, you can find a lot of them online on Reddit, on Instagram, or whatever. This is very readily, it's really easily available. But having those with labels, so saying what is in the picture specifically, that's very hard. I mean, and you usually need human annotators to look at the images and add labels. So that costs money, that costs time. That's very difficult to obtain. And similarly with medical, probably with medical data, you could have access to a lot of images from data banks of, I don't know, patients, but having a very annotated with information about, okay, there is a tumor here or there is something else here. It takes more time because you need someone else to analyze the data and add information. So that's the biggest problem, having access to those categories. And so when it's difficult to obtain labels, usually what you end up doing is using a semi-automatic labeling process, and that's for instance, if you already have models that can categorize images, you could use those to do a first approach, like a first process of the image. So giving that to a model that gives you categories, and then having someone else check, like double check if this is correct or not. So it speeds up the process because there is already a label attributed to the image, and you just have to, if it's correct, just skip and look at the next one. But if it's wrong, then you have to give the right information, but it can speed up the process. And one question that we can ask is, do we really need all those labels for all of the images, or can we have a method that work if we have part of the data set that is unlabeled, for instance? And so have a few examples that are that have good annotation that we can leverage to train a model, and then have extra data that is not labeled, so like raw data, like just images without categories, but still manages to improve the performance of a model rather than just using the labeled part of the dataset. Otherwise, I mean, having extra data is not useful if we just need the labeled part, and we can do with that. But okay, finding a method that is kind of hybrid and work with both. So this is basically the method we're going to talk about today. And the names that you have to remember is semi-supervised learning. So semi-supervised learning means that you have both data that are supervised. So that's what is semi-supervised, because it's half of them is supervised and another part is unsupervised. Few-shot learning, zero-shot learning, and supervised learning. I'm going very fast on these because we'll have I'll detail all of them specifically. And yeah, we'll see if we have time, we'll see like several kinds of unsupervised learning methods. Okay. So let's start with semi-supervised learning. Just as a note, I'll give some example of methods. They exist plenty, and it's active research. So new methods arrive every day. I've tried to like pick and choose the simplest one and the one that are maybe easiest to understand, and we'll focus on those. But yeah, having this like keyword, if you need that somehow at one point, you can just look for that keyword in literature and find a lot of work. Okay, so let's start with semi-supervised learning. So going back with our example, the semi-supervised is when you have, so here we have a data set, and as you can see, some of them, the image one has a category that is associated to this. But so, category is the same as label? Yeah, so label can have different forms. If you're talking about image classification, and that's why I'm saying category. So image classification, you have an image and you want to predict what object is in the image. We typically call the label a category because it corresponds to the category of objects that appears on the image. If your task is, let's say, image segmentation. So image segmentation, I don't know if you remember this picture where we had, yeah, the skateboarder with colors, like patches of colors, like contour of the different objects. Then you need more than just category, because you also need, like, for each pixel, is the human, is the skateboard, is it the background? You need more information. So what I'm calling category here is the label that we associate with image classification. I'm focusing on image classification because it's what we saw last time, and maybe it's what's fresh on your mind. But this could be applied with any kind of label. Yeah, a good question. Thank you. So here we have data, so we have images and we have categories. And some of them, like for instance, the second image, I put like a question mark because this is unavailable and we don't really have category for this one. So this is an unknown image. And so we can have both in a data set. And that's what's difficult in this case, because so part of it is labeled, part of it is unlabeled. And the question is, how can we leverage both? Yeah, so that's what I was saying. And so the method we're going to use is called pseudo labeling. And so pseudo labeling, what the pseudo labeling process is we're going to try to infer or predict. So first learn only with the ones that have categories, because then we can go back to the method that we saw last time. And then with the model that we get, we can try to predict the missing categories here by just evaluating a model of these images. And once we predict, we're going to use, that's what you call pseudo labels. So these are labels that are predicted. So they're actually ground truths, actually the truth of the category, but we can use that as a label for a second pass where we're going to use everything, all the images. Some of them will have the real one, the real category, and some of them will have a predicted one. And then we do that like iteratively. We repeat this process. I'm going to go into more detail. Okay, one caveat or one important information with this method is that all classes must have annotated images, which means that some images can so like this one not have a category, but if we have, let's say, two categories, two possible categories, so if images can be in C1 or C2, we need examples for every category. So we need examples of images that correspond to the C1 object, and we need examples of corresponding to the C2 object so that it can work.
So this one is like that we have a small like training set and a test set, and then the model learns from the test set. So it is like that.
A bit like that, except it's not really a test set, but it's like a, I don't know, a second train set that has no labels. Yeah, but exactly. It first starts with a small train set with everything is annotated, and then once it's trained on that, it will test or evaluate this other test that has no labels and annotate this, and then we can like use that as an additional information for our second pass of training. So a new model that we start train from scratch again, but with this added data, and we retrain everything with that. Okay, let's. I'm going to go into the various steps. So these ones are unlabeled, and so we're going to split this one. And also, I call this one DL for dataset labeled, with only the one that are labeled. And the second one I call DU for the unlabeled datasets with the one that are unlabeled. Okay, so I split this original dataset into two. Then we use the DL1, so the dataset with everything that is labeled, and we train this classifier. So our image classifier that we saw last time, we train it on this. And then so this second step is that we use this train classifier F to predict the category for the missing labels, the images with missing labels. So we create this second one. So I call it DL2 for second labeled dataset. So again, everything is labeled here, but 2 because now it's bigger and has predicted labels for the one that have missing label. And then when we have this, well, we can train a second classifier on this dataset here. And the hope is that even though this has been predicted by a previous one, then this one will get better. And actually, we have, under certain conditions, we can have we can be certain that the function will not get worse with these ones, so they will only get better or the same, but at least we'll gain information by doing this process. And so here again, you can imagine that we can continue this iterating. So now that we have F2 that has been learned with this one, we can recreate DL3, so a new data set, where we use this new classifier that we trained on the previous DL, so on DL2, and relabeling these ones with this model. And hopefully they will be even better. And we can continue over and over until somehow convergence, until we see that there is no real improvement on the model we get. Okay, is that clear? The process is clear? Yes. Exactly. Okay, online I didn't say, but feel free to interrupt or send messages in the chat. I'm trying to keep track of it. Yeah.
So here it is like relabeling the unlabeled images.
Exactly. Yeah. Okay. So that's the method basically for semi-supervised. That's one method for semi-supervised learning. And just to give you a bit of a recap, so when to use this method, so it's useful when not all images are labeled. So you have access to lots of images. Some of them are labeled, some of them are not. But so the condition to use that is that every class must have some labeled images. Okay. And what to do if it's not the case, then you're going to need one of the other methods that we're going to see later, right? Namely zero-shot learning or unsupervised learning. And yeah, so this is just a recap. One condition also is that it still requires many labeled examples for each class function because as it is an iterative process and you use the classifier that is trained on the previous set, you need somehow that the classifier learns something from the few examples. So if there are really too few and you can't really learn anything, then you can't bootstrap your process and you will never improve really. So this is kind of also another caveat of this method. Okay, so now we'll go to the next section if you don't have questions, which is few-shot learning. So few-shot learning is useful when your dataset is completely annotated. So differently to before where we had some that were annotated, some were not. Here we have just a few examples, but they are all completely annotated. And yeah, and every class has just a few training examples. So basically, we have a very small data set. Everything is labeled, but we have a small data set. And in particular, we use a notation n-shot learning to say that each class has exactly n training examples. So 5-shot learning means, so I'm giving an example here. If you want to classify, I'm moving away a bit from images, but here text is the same. So if you have emails and you want to classify if it's spam or not spam, if you do 5-shot learning on this, that means you have 5 examples of spam emails, 5 examples of normal emails, and you will try to learn your model from that. One-shot learning, so example with a dogs and cats classifier. So a classifier that takes images of cats and dogs and say if it's a cat or if it's a dog. One-shot classifier would be, okay, I give you an example of a dog, an example of a cat, and from that you have to learn how to differentiate one from the other. Okay, and then you can imagine at the end, like what happens if we have 0-shot, so no examples, and that's going to be another method that you're going to see later. But let's now focus on few-shot. So there are several methods. Again, plenty of methods for this. We are focused on 2. One data level approach and one metric level approach, learning approach. And actually you can combine the 2. They're not exclusive. They're just ways of making it work. One on how to deal with data and improve your data. So if you don't have a lot of data, maybe you can make it that the data is more relevant. And another one is a metric learning approach, which is really the approach of doing the few-shot learning classification. So data level approach. So what to do when you don't have enough data? One maybe stupid answer, but I'd say it. It's to get more. And when I say get more, it's probably if you don't have a lot of data, it means that you can't really have more, but we're going to try to artificially get more data. And the tricks that we're going to use, the main trick that we're going to use is called data augmentation. And also we're going to talk about transfer learning, but mainly here we're going to talk about data augmentation. So how to augment your data set from just, so if you have one image, how can you have many? And it's, I mean, the idea is very important, but it's quite simple. It's to basically do transformation to your example, to your image. So if you have this original cat image, remember last time we saw that an image is just pixel, and pixels are numbers that represent red, green, and blue values. So if you give one image to the classifier, it has a fixed representation. And one way of changing it a little bit would be to apply transformation to this. So like, what if you do a crop or a zoom? So now we have a new image. I mean, it represents the same thing, but it's not exactly the same pixels. So location changes and yeah. So if you like compare like pixel values here to the pixel values here, they're radically different. One other thing you can do is vertical flip. So you had one cat looking one way, and now we have a cat looking the other direction. You can change the saturation, the contrast, and you can imagine many things like doing this kind of transformation, maybe adding noise or changing colors or this kind of thing. And you can combine them. So now you had one image, you artificially created many, and remember, each of them represent the same thing. So they each have the same label. And so for each class, if you had one image, now you have 4 that represent the same class. So this is good for image classification. Just a small note, if you're doing something else like image detection, imagine you want to detect the cat. So you need like a box around the cat to know where it is. Remember that if you do a transformation, it will also transform where the location of the cat. So you also need to do the same transformation to your label. So here, if you had the box that is here, then now the box is a bit different. It's here. And here it doesn't change because it only changes colors. But whenever you change the location of objects in the image, you have to be sure that you transform your label correctly. But okay, we're looking at classification. There's no problem with that. No need to change your classes. So that's one way of, that's a first trick. And yeah, there exists some good useful libraries for that, like Augmentor or ImGaug. You can find them online, and you give basically one image and a list of transformation, some probabilities, like how probable I want this transformation to happen and so on. And it just makes you many examples from one image. Our second trick is transfer learning. So transfer learning is a bit cheating. I'm saying cheating because I said we're going to do few-shot learning with only, I don't know, one example per class. And this is true. We're still going to do that, for instance, with cat and dog. But you also know that online there exist many datasets that don't necessarily show cats and dogs. So datasets that show, I don't know, many kinds of objects. And the idea is maybe knowing or learning how to classify those objects will help for the new one. So imagine you want to classify cats and dogs, but you have, I don't know, a data set that represents many animals except cats and dogs for some reason. Maybe learning how to differentiate different animals will help because you will learn what a head is, a tail, many features in the image that are important to differentiate different animals and that are very general and not specific to these animals, but could be applied also for cats and dogs. And so learning on those will help for your new task. And so that's what we call transfer learning. Transfer learning, basically, because you're learning on something and then you're transferring the knowledge that you learn on these new examples. And it also goes with the vocabulary of pre-training. So pre-training a model means training the model on one data set, and then once it's pre-trained, you will keep the learned model, but you will, what we call fine tune, is continue training on your example. So you pre-train the model on one data set to gather knowledge on this data set. And then you continue the learning only on your own data set with a few examples. And this new learning hopefully will keep information that it gathered before and just adapt it for your own task. If you have a very large network, so many layers, very, very deep, what you often hear is that the first layer will be very abstract information extraction, like Gabor filters, or like, high frequency or low frequency information in the image, maybe some line detectors, some edge detectors, these kind of very simple things. And then the second layer would be finding shapes, so like maybe circles, waves, patterns. And then the higher level at the end are the one that are very domain specific. So maybe like a cat detector or a dog detector. And before that, you had maybe a face detector and a leg detector and so on. So it is very hierarchical. And so if you pre-train your model on one data set that is very large and has lots of information, even if it's different from what you want to do, the first layers, because they're very general, they could be used for your own task. And so what you usually do when you're pre-training and then fine-tuning is not continue training on everything, but you could say, I'm freezing, or I'm stopping learning on the first layers because I know they learned very specific, very generic information, and I don't want to change that. And you only train the very last layers that are data set specific, let's say, to be on your task. Okay, no, these are various tricks you can do. So this was for how to deal with data. So first ID, data augmentation. We have an image. We can make transformation to get new images. Second ID, we can transfer the learning from other data sets they can find online, and then use that and to my advantage for my own data set where I don't have a lot of examples. And now we're going to look at really like how to perform the few-shot learning classification, or one way. And this way is to define some kind of distance on image space. So what does it mean? The question is how to compare images. So we have an image here, we have another image. So you know how to do a distance for numbers. So if you have, I don't know, 3 and 4, how to do a distance, you do subtract them. You can also do that with very, I don't know, like vectors. So in two-dimensional space, how to do distance between my computer and me. I'm measuring basically where I am, where the computer is, and also do a subtraction. And then sum the various components. But how to do this for pixels? How to define a good distance measure for images? Because, okay, these two images are far. If we look at pixels, so if we compare individual pixels from one another, they are far. But what happens if we have this, for instance? This is the same image, just cropped or a bit smaller. But now if we compare pixels, they're all different because it's a bit shifted. So we have a high distance, but actually what we want is something that is class dependent. And so if we have high distance in this case, then that's not really what we want. We want something that is close when the objects are similar, even though the pixels are different, and far when the objects are different. So here we want the distance to be very far, here we want it to be close, and here we also want it to be close. I mean, of course, it's further away from this one because it's not the same cat, it's not the same look. But if we want to use it for classification, we want actually this distance to be close because they represent the same object. Okay, so the way we're going to do this is by leveraging what I said before with the transfer learning. And before doing that, we're gonna define what we call a feature vector. So what if instead of comparing images, we compare feature vectors? So a vector, not a vector that represents the flattened image. So remember last time we said, okay, we have an image, we can just look at each pixel and flatten them and put one pixel after the other and we have a vector. No, this is not good because that's the reason I said just before. Now, what we want is to have a feature vector. So a vector that represents high level information about the image. So I don't know, the type of object it is, the location of the object, maybe some color information, pattern information, like texture information, this kind of thing. And then when we have this vector, then it's easy because we can just do distance on this vector, like a Euclidean distance on this vector, and then we have our answer. And so we shifted our problem from how to find a good distance to how to find good representation of images. Because if you have the good representation of images, then the distance is easy. We just do a Euclidean distance on this representation. Okay. Is that clear? Okay. So now I found a method to find good representation. And of course, we're doing the machine learning course or the AI course. We're just going to learn it. We're going to train a model to find good representations from images. And so how to do this? I don't know if you remember last week, but we saw a lot of different architecture of models. And among those, we saw ResNet. It's a very, very typical network that you're going to see a lot because it's used a lot. And so that's what we're going to use today, the ResNet architecture. And if you remember the transfer learning method that I was just talking about, where you were training your models on a data set that exists and learning information on this, that's exactly what we're going to do. So we're going to use another data set, let's say ImageNet, that exists. So lots of examples of natural images. And we're going to train our ResNet on images. Actually, we don't really need to train on image or model on ImageNet because there exist already online tons of already pre-trained models on ImageNet. So that's for free. You can just download them and use them. And so, as I was saying before, the structure of the models is hierarchical. So the lower layers are they can classify, let's say, like frequencies or lines or circles, these kind of things. Then here more evolved patterns, maybe waves. And then later you can have, I don't know, like textures, like and I don't know, legs or heads or whatever. And at the end you have very high information, very specific classic information. And then at the end you have a max pooling and then one linear layer here that predicts from this representation the class. And it's a one linear function. So that means you can linearly predict from your representation to the 1000 classes of ImageNet. And so that representation before that is pretty nice because this representation is already pre-trained. So it's already a good representation. It's small. I mean, small. It's like 1000 value, but it's smaller than having an image that's, I don't know, 500 pixel by 500 pixels. And it can be linearly classified into lots of classes. So it contains very strong semantic information about what object it is. And so that's usually what people do. They use that as a feature vector for representing images. So now it's easy. You take your ResNet that's already trained on the internet, you just download it. You feed it your image, and you don't look at the output of the model. You look just one layer before, and this is your feature representation. And now that we have this, so we can compare images. So we have one image, it gives a feature representation through our ResNet model. We have another image, same. And then we can compute the distance between those two vectors. And this will tell us how far away the two images are. And what does it mean that D is small? Well, it doesn't mean that the pixels are very similar, no. It means that the images are semantically similar. So they represent the same object. Okay, now that we have this, how to classify images, that was the original goal. Okay, now I imagine that you have, I don't know, here I represented two, but like two examples, two images for each class. So C1, C2, C3, let's say cat, dog, and car, three different classes. We have two images for each of them. We can get a feature representation from our ResNet that is already trained on ImageNet. You download the weights on the internet and you use that to get feature representations. Now you have two for each class, two feature representation for cat, dog, and car. And one way of doing it is to get class representatives. So class representative would be one vector that represents the entire class. And here the way I'm doing it is to average them. So if you have two representations here for cat, remember the hope is that the feature extractor did all the work. So the representation already semantically represent the cat. If you have two, you can average them and it kind of make like a prototypical representation of a cat. Okay, it doesn't represent one image, it represents this kind of average cat. And if you have two examples, then it's a small average. It's average between two cats. But if you have like say 5 examples, then it's a more representative thing. And the more examples you get, the better it's going to be. But I mean, the whole point is to not have a lot of them, but you don't need a lot of them. You just have this prototypical representation of your cat. Same thing here. You have your prototypical representation of your dog and of your car. Does it make sense? Again, remember how to classify. We get representations and then we do distance. But now we actually have representatives. But it's the same. I mean, the vector here, same dimensional. It was just an average between several, but it's still the same feature. We can still compare the two and do a distance. So whenever I want to classify a new cat, I say this is my new cat I want to classify. I get from my ResNet my representation of the cat, and then I can compare this feature with my class representatives. And so I compare it with my cat representative, I get one distance. I compare it with my dog representative, I get another distance, and I compare it with my car representative, and I get another distance. But I mean, this representation is semantically similar to cats. So hopefully the distance, the lower distance will be towards the class that you want to classify. And then that's how you're going to do it. So you do the distance from this example from each of the class representatives, and the one that gives the lowest distance is your prediction.
The class representatives are the average of the distances among the members of that same class.
Yes, on your training set. Yeah, exactly. And because D is doing a distance between an image and class and actually looking at the compatibility of this image with each class, we call it the compatibility function. So it gives compatibility from this image or representation of this image to each of the class representatives. So the number you get is actually how compatible the two are. And the one that is the most compatible is the one with the lowest distance. So, okay, that was a few methods for how to deal with a few examples. Yeah, as I said, many examples, many methods exist. Some other, if you want to, I mean, this is just going further. Yeah, I put stuff here whenever one day you need that, if ever. And you go back to the slides and you have some ideas about how to do it. I'm going to skip. Yeah, and this is just next section, so I'm just going to mention it. Well, if we don't even have examples for some labels, that's called zero-shot learning, and we're going to talk about this after. Okay, a bit of a recap. What do we need to do few-shot classification? We need a data set is completely annotated, but it's small. And most classes should have very few training examples. Or you can have many. I mean, you can apply the same method I've just described with many examples. If you have 50, 100 examples per class, it's fine. You can do that as well. It works. And we've seen two main, I mean, I said method, but I wouldn't say method. It's more like two main, um, how do you, I don't know, two main things to do. I don't know. I don't have the word. One is to improve the data set somehow, so augment the size of data sets, either by transformation or by using already existing data set online and do like this transfer the information from one to the other. And then we talked about how to do the classification in effect using this metric approach. Okay, any question on future planning? Okay. Now zero shot. It gets even more difficult now because we have some examples where we don't have access to labels. But I'm going to preface this by just an example. And I'm going to give you a picture here and hopefully you don't know what this word means. If you do, then it doesn't work. But if you don't, great. I have this picture here and my labels. So basically our goal is to do zero-shot classification on this. We have this image and we want our three categories are this, and we have to classify this with this. Well, it's hard. It's if you don't know these words, it's impossible. But what if now I give any additional information, which is as like a description. And even though you've never seen these words before, you've seen words in the description and you know words of the description and you know how to classify those words from an image. And then you can, I don't know how to say this word, unanimously say which one it is, right? And guess that actually this one is classified as the Namakuni. I don't know how to say that. And so that's the goal. Like that's how zero-shot learning works. You've never seen this particular example or this particular instance of class, but still leveraging some additional information. So here a sentence. You will be able to find which one is the correct one. So to recap, zero-shot learning is to recognize images from new unseen classes, but having information on the unseen classes. That information has to be related to what you already know, right? Because if I gave you here sentences about things you didn't know, then it wouldn't be better. So here I've highlighted in bold what's important, like ginger, because we can see the ginger here, beverage, we can say that. These you already know. And of course, a model, if you want to give information about new classes with this, it needs to know things before. It needs to know what the beverage is, it needs to know what ginger is, it needs to know what the fish is to classify these type of fish, or it needs to know language, for instance, to classify this. So you need to know additional information about hard instant classes, but you also need scene classes, which have label. So the vocabulary is, yeah, seen when you have labels for these images, unseen when you don't have the images, but you still have the class description or the description, the labels for those. And the semantic vector is this extra information that you give to all classes. So it was the description I was giving before. Here we say semantic vector because in our case, I mean, it can be anything. And yeah, so it usually is just a vector, and semantic because it gives semantic information about what each of them are. Okay. Then you need one semantic vector per class. So both seen and unseen, every one of them has to have a semantic vector. Okay, I'm starting with introducing a new dataset, which is called animal with attributes, AWA, and the second version of it. It has 50 different animals in the dataset. There are 50 different animals in the dataset. 40 of those are seen, so you use them for training. So you use the images for training. And then you have access to semantic vectors for the 50 animals. And so you're going to use 10 of those for testing. So you will not use them for training and use only the images for testing your model, and use the attributes during training as well. And so the attributes, the semantic vectors, they are 85 visual attributes that are colors, textures, and abilities of the different animals. And it's not, do I have a slide? Yeah. So for each image, you have this kind of information. So let's say a zebra, for instance, you know that it can be black, it can be white, it's not brown, it has stripes, it doesn't live in water, it doesn't eat fish, and whatever. You have like 85 of those attributes. And so here they are binary, but they are for each image. Okay. So let's say now you have a brown zebra, then you would have yes for the zebra and brown. Okay. So that it's not class dependent, it's image dependent. It depends on really the image. It's annotated for each image. But I was saying before, you need one semantic vector per class, not per image. I mean, this other set gives more information that we actually need. What we typically do is average for each class, average all of the information that we have to get like an average representation of the zebra. So if we have like a binary thing like this, okay, my blue classes are the one that are seen classes. The zebra is the unseen class. And the different columns are the attributes. And so here, if I have examples, I was saying it's binary before. So horse, let's say it's white, it's black, whatever. Actually, what we use is, this would be probabilities or proportion in the data set. So 60% of the horses are black, white, 40% are white, are black, 0% are orange, 70% are big. Yeah. And when we choose I mean, this data set we don't have to choose because it's already done. But imagine you have to make the data set or choose attributes for those. You have to be careful about the things you use to discriminate them. Okay. Why? Because if an attribute discriminates everything, so if it's here for everything, then it's not discriminated. And if I add a zebra, I won't be able to use that information to know if it's a zebra or not. Because if everything is white, I will not learn nothing about what white is, and just that it's always white. I don't know what white is, but it's always white. And so I won't be able to use that to classify my new class, which I haven't seen. And on the other side, if it's too discriminative, then the model we just learned that, okay, if it's orange, it's a tiger. Because I mean, that's what it is, right? It's very discriminative for tiger. So it's very easy to classify tigers from having orange, because whenever there is orange, there is tiger. And I'm not going to learn what orange is from that. I'm just going to learn orange is tiger, and not that orange is a color. Because when to learn attributes or to learn to decipher attributes, I need to see. I need to understand like different versions, like different examples of the same thing that have the same properties, and or that don't have the properties to infer what orange is. I mean, you know what orange is, but the model doesn't, right? I'm expecting. Imagine you don't know what it is. If I just show you examples with horses, tigers, and skunk, a skunk is buffet, by the way. You will just learn that orange is tiger, and that's it. You will not learn that orange is actually a color. But if I give you an orange, actually like the fruit, in addition to that, so you have two references for orange. Okay, what's the common attributes in the tiger and the fruit? Like, okay, maybe it's actually the color, because that's what is in common. So if it's too discriminative, you will not learn anything. You will just associate one with like a property with the class, and that's it. Was I clear? I feel like I was a bit rambling. Okay. Okay, so that was, yeah, properties, probabilities. Well, we don't see anything here. We zoom in. No. Can we zoom in? Okay, let's do this that way. Ah. So this is just a plot of each of the animals according to two attributes. So I don't know if you know what a PCA is in PCA, in ACP. Yeah, principal component analysis, analyse en composant principal. It's a method to, if you have a high dimensional space and you want to extract dimensions that are important for that differentiate that increase the dimensions where the variance across your classes are important. Yeah, this method allows you to do that. It finds dimensions in your space where the variance between your examples is the highest. And so here I applied this for semantic vectors, and each point is an animal. I can try to zoom, like for instance, we have a horse, a deer, a zebra. So the blue ones are the unseen classes, I think, and the red ones are the seen classes. What we see in that PCA, what I kept actually just a few examples, is that one dimension is the grazers, or like the vegetation and hooves. So if we look at the top, we have like the sheep, the deer, like all of those animals that hooves is like sabot, or all of these animals which have hooves and eat vegetation. And at the bottom, we have the opposite, like we have animals that eat meat. And yeah, and on the other axis, you have big water and swim. So on the left, you have like small things like a bobcat or a fox. And on the right, you have very large things like a whale. But it's also related to somehow water. So things on the left are more animal, land animal or earth animal. And on the right, you have like what animals that live in water. And if we go up, remember here we have things that at the bottom is like at the bottom of the screen, things that are opposite to vegetation and hooves. If we go up, we have water and vegetation and hooves. Well, we don't have a lot of things, but we have hippopotamus here, which is at the same time in water and has hooves. And I don't know what an hippopotamus eats, but probably vegetation, according to this. Yeah. So this is just to look a bit at all the attributes and how each of them are clustered. And the hope is that, yeah, you see blue dots close to red dots and in between, and you don't just have one side blue dots and one side red dots. Otherwise, you won't be able to decipher anything. You need, if you want this to work, you need both everywhere. So here you have this one that can be related somehow to this one, and same here. Okay. Let's go back to this slide. Okay, so let's recap a little bit. We have some examples, some images that all correspond to the scene classes. We have the semantic vectors for the scene classes, but also this extra unseen class or several unseen classes. And then we somehow want at the end to give any kind of images, even from the fifth class, and our classifier needs to classify all of those after training. So question is how to use the attributes. So here we have our ResNet model. It predicts, so this is from, this ResNet we were talking before that learned on ImageNet. We give an image, a turtle, give the prediction of the class turtle. This is a scene example, a scene image. You have your attribute space. So all of the, different attributes, your semantic vector. And you look at turtle, where turtle is in your attribute space. So turtle, it has this kind of, I don't know, it eats grass, it's in water, like all of these attributes, all of the things, and you can place it in your attribute space. And you can do that for all of your classes, like rifle or all of them. And actually, so this is a representation of your semantic vector. And what you can do is instead of predicting the class, you can try to predict the semantic vector. Because now if you predict your semantic vector, you're not tied to a specific set of classes. Because if you train your model to classify from, I don't know, 10 classes here, and that's it. If you want to classify a new one, you won't be able to. You would, I mean, you don't have this option. But if you predict the semantic vector instead, then you can classify anything. It's just a matter of knowing what the semantic vector is for your new class, and this is your target for your new class. And then you can use a bit like we've seen with few-shot learning, this kind of distance, remember this distance and this class representative thing, where your semantic vector become this class representative. And you can classify using distances to this class representative or to this semantic vector. Okay, and so here I'm just showing that you can backpropagate. You use the backpropagation of algorithm here from the semantic vector to update all the weights of your model. So instead of predicting the class, it predicts the semantic vector. Speaking this. So yeah, this guy. Remember in few-shot learning, how you were doing classification or comparison between classes with this distance? Well, exactly the same. Now we can predict our semantic vectors. Now that we predict our semantic vectors with our model, we can just do a distance to that class representative or semantic vector of the class, and do that for each class. And this is what we're going to use to classify our new classes. Because if we have learned how to do this for our scene classes, the hope is that we've extracted general enough information about how to transfer one image to a semantic vector. So understanding what white is, what black is, what big is, basically. And when you have a new image, we're not trying to predict what the category is. We're trying to extract features of this category, of this image. And so even if it's new, we know what white is, what black is, what big is, so we can predict that. And if we manage to predict that, we can just compare that with our ground truth for that. And the closest one, hopefully, is the one that we want to classify, what to predict. And again, okay, I've wrote that with a very funny notation here, which is a scalar product, a dot product. But this is our compatibility function again. It's just multiplication. We are projecting our image features towards the feature vectors, the semantic representation. And so to do that, we just do a basic multiplication by matrix. And we can compare that projection with the actual semantic vector, S of y. And this gives us our distance. And again, we call this compatibility function because it tells us how compatible our prediction is with the semantic vector. But okay, what you have to remember is we've shifted from trying to predict a class to trying to predict attributes of an image. And if we're able to predict the attributes of an image, then we can infer what class is by looking at our semantic vectors that actually tell us that gives us the class for certain types of attributes. Okay. And I'm going to skip this. Just to recap, deep learning is trying to recognize images from new unseen classes, but we can't do that without any information. What we have is this additional information on how to classify this unseen class, which is our semantic vector or our attributes that represent each class. And we've seen this discriminative approach using the compatibility function. You can look at the slide if you want to know more, but you can also do that with in a generative way. Yeah. Okay, so now the question is what to do if we don't even have labels. So until now we had some kind of labels. Here we had the semantic vectors that could help. The question is what to do if we don't have labels. And unfortunately, I think we don't have time for that. And I think I would prefer to make a little break and do the practical session on what we've seen. And maybe do, after the break, a little overview about what unsupervised learning is. So without going into details. In the previous instance of the course, we had more time for this lecture, but unfortunately, we have cut a bit of it. So yeah, let's have maybe 10 or 15, 10 or 15 minute break. Like let's go back at maybe like 20, like 3:20, 15h20. Online, you can also don't hesitate to send questions on the chat or whatever.
C'est bon. D'ailleurs. Ouais, elle a expliqué, oh non, oh, c'est mignon, c'est chien et tout, et tout, avec des affaires, c'est non. Oh, regardez, c'est chien qui sont rentrés par le tour. Ah oui, c'est marrant. Donc, pas grave, c'est une bonne affaire de vie. Et du coup, ils vont continuer. Ça. Ok, c'est la qualité, c'est la qualité. C'est ça. Ah oui. C'est mignon. Breaking news. Ah voilà, ça c'est trop parce que la réalité là, c'est méchant. C'est une amitié. Voilà, c'est des choses. Ah oui, ça c'est une amitié. Mais c'est une bonne là. Ça, mais c'est bon, on va se parler de tout le monde. Ah non, mais c'est ah, Non. C'est que là, oui, je vois des trucs. Et maintenant, les détournés, les gens, ils sont vraiment, non, non, c'est pas. Ah, c'est les trucs de, ah, mais,